Hello everyone, let's go ahead and do our experiment 10, post-lab calculations. So in this experiment, we're going to find out concentration of an unknown using Beer's law. Okay, so in this experiment, you will learn how to carry out dilutions if you are given a stock solution. Okay, we're going to be using M1V1 equals M2V2 to calculate the diluted solutions concentrations from a stock solution. And also we're going to learn how to use spectrophotometer and use it to determine the absorbance of Allura red solutions. Allura red is the red dye 40 that you normally find in red color beverages. And then we also learn Beer's law, and which is the relationship between absorbance and concentration. And again, we are going to construct a calibration curve so we can review how to draw a calibration curve and how we can use that to find a concentration of an unknown. Okay, so we are going to see how the light is going to interact in this experiment. Okay, so you can read the introduction part of the lab handout. It talks about how light interact with matter, but in this experiment we are going to focus on the spectroscopy to deduce the amount of a particular molecule in a solution. And it turns out that there is a direct relationship between the number of dye molecules present and the amount of light absorbed. Meaning, Allura red is a colorful dye. So these colored compounds, they can absorb light. If you put this into a little cuvette is the little glass container normally we use to put it in the spectrophotometer cuvette. You put that dye solution into a cuvette, you put it in the spectrophotometer, and then you let the light pass through it. Okay, and then when the light passes through it, depending on the number of dye molecules, it tells us what is the absorbance. Okay, for example, if there are 10 dye molecules present, if you have 10 dye molecules, let's say there are 10 on here, okay, 10 dye molecules present, and the amount of light absorbed is also going to be 10 photons. And if there are 100 dye molecules, it will absorb 100 photons, like that. So in other words, concentration is directly proportional to the absorbance of the light. Okay, and that relationship mathematically given in the form of A absorbance equals epsilon BC, and we call this as the Beer's law. Here A is the absorbance, epsilon is a constant for a particular dye, and for the Allura red that would be a constant. And then here B is the path length. What is the path length? Path length is the distance from one inner wall to the other inner wall in the cuvette. Normally it is designed as 1 centimeter. So B is 1, and here the C is the concentration. Okay, so if we draw a graph, y equals mx plus b. So the concentration going to be the x-axis, and then the absorbance going to be in the y-axis. So we can find out the mole extinction coefficient from the slope of the calibration curve, and then we can find out if you know the absorbance of an unknown compound, then we can find out the concentration by using the equation that we get from the graph. Okay, now to construct the calibration curve, we all know that we need to make a series of solutions. What we're going to do is, since the absorbance is going to change with the concentration, we use the Allura red stock solution to make diluted solutions. So let's see how we're going to do that. So you will be given Allura red stock solution, and its concentration going to be 3 into 10 to the negative 5 molar Allura red, and you are going to prepare 6 test tubes, 1 2 3 4 5 and 6. Okay, and you're going to be adding a certain amount in milliliters. Now for the first one, you don't add any Allura red. You're going to keep it only with water. So I will go ahead and label these solutions. So this is going to be your number 1, 2, 3, 4, 5 and 6. So for the first one, no Allura red. But for the second one, you add 2 milliliters of Allura red. 2 milliliters. Third one adding 4. And then fourth one add 6 milliliters. Fifth one 8. And then the sixth one you add 10 milliliters. Okay. And then as you can see, since we have different amounts added, when you add water to this one, the concentration is going to change. Okay. Now we're going to be adding certain amount of water. So let's add water. So the first one you're adding 10 milliliters of water. So then it will be 10. No Allura red in it. And for the second one you're going to be adding 8 milliliters of water. 6 milliliters of water. And then to this one 4 milliliters. To this one it would be 10 and no for the last one. Excuse me. Okay. And when you add these volumes, all of these going to have 10 milliliters total volume. Now, do you think the concentration of the dye is going to change in these solutions? Yes, it is, because the concentration is number of moles over volume. Since the volume changes and we did a dilution, the molarity changes. So since this is a dilution, we can use our equation M1V1 equals M2V2. So initial concentration, the stock solution can be considered as M1. And our M2 going to be, not M2, V2 going to be the volume of Allura red we have used. So for the first one, we did not use any volume. So then concentration of Allura red would be 0. But for the second solution, you take 2. So V2 going to be 2. Not V2, V1 in fact. Should be V1, okay? V1. Let me do. This is the second solution. So the V1 going to be the amount we used from the stock solution. For the first solution, 4. Second one, for the first solution, 2. Second solution with the Allura red 4. And then 6, 8, 10, like that. That's going to be the volume. And then we also know the M1, we know the V1. What's going to be our V2? For all the cases, V2 going to be 10 milliliters because that's our new volume. So we can find out M2. Okay, let's see how to do that calculation with that equation. M1 V1 equals M2 V2. M1 3 into 10 to the negative 5. Volume 2 milliliters. And M2 we don't know. V2 new volume 10 milliliters. So then the M2 going to be 3 times 2, 6. 6 over 10, 0.6. So that is 0.6 into 10 to the negative 5 molar. That is the concentration of the second solution, which we added 2 milliliters of Allura red. So likewise for the third one, what you're going to do is instead of 2, you use 4 milliliters. That's the only thing you're going to change. So 4 times 3 is 12 over 10. That's going to be 1.2. So M2 going to be then 1.2. It's going to be 3 into 10 to the negative 5 equals M2 times 10 milliliters. M2 would be 1.2 into 10 to the negative 5. So likewise, for the fourth solution, what's the volume of Allura red we use? We use 6 milliliters. Right? So you change. Here it is 2, 4, 6. If it is 6, 6 times 3, 18 over 10, 1.8. So the M2 for the fourth solution would be 1.8 into 10 to the negative 5. So likewise, you can calculate all 5 solutions concentrations. But the last one, where you added only Allura red, since you did not add any water, it will remain as 3 into 10 to the negative 5. Okay, so please do these dilution calculations using the dilution equation and see if you also going to get these numbers. Okay, and then once you get these calculations for the concentration, you have to write it down in this table. Okay, so when you find those values, for the first one it's 0.6 into 10 to the negative 5, second one 1.2 into 10 to the negative 5, third one 1.8 into 10 to the negative 5, fourth one would be 2.4 into 10 to the negative 5, and then the last one we did not add any water, only a Lurarate, so the concentration didn't change. And then the absorbance values were given to you in the data sheet. So you can go ahead and write it down here. For the first one, 166. For the second one, 0.340. And then 0.490, 596, 774. Okay. So you use these data to construct a calibration curve. You're going to be using concentration as your X values and then absorbance as your Y values. Okay. And then once you get the calibration curve done, you're going to find out what is the best fit line and then the equation for the graph. And you will also notice that in your data sheet, you are going to do a dilution for the Gatorade sample. Why do we have to do a dilution? Because it's highly concentrated. If you just do as you receive the Gatorade, it's going to give us a higher absorbance. Normally, the Beer's law works well if it is absorbance is less than 1. For example, so if you draw a graph between concentration and absorbance, we are looking at a linear relationship. A equals epsilon BC, Y equals mx. It's a linear relationship. So this linear relationship obeys if the absorbance is less than 1. But let's say if it is 1 here, as soon as it goes above 1, it deviates from the linear relationship. So because of that, we want to keep all our absorbances less than 1 to use the Beer's law. Okay. So your Gatorade, we need to dilute it. You take 1 milliliter and then you add 9 milliliters of water to that. Make a diluted solution. So now the diluted solution is 10 milliliters volume. Okay. And for this one, you put it in the cuvette and you find the absorbance. And absorbance come to be as 0.357. You find this number in your data sheet, 0.357. Okay, now since we know the absorbance for the diluted unknown, you can plug that value for the absorbance in your equation that you get from the graph, and we can find out the concentration of the diluted unknown. And then since our dilution is 1 to 9, again we can use M1V1 equals M2V2 to find out the concentration of the undiluted unknown. Okay, that's the plan. Now, this is the calibration curve that you will be getting if you plot the x-axis versus y-axis, which is the concentration and absorbance. So this x-axis is going to be your concentration, y going to be the absorbance. Okay, and when you are inputting the data into the Excel, make sure that you put it in this proper format. Like if you want to do exponent, just do it like that, 6 and then e negative 6. Don't do it like this, 6 into 10 to the negative 6. That will give you a wrong equation. That would not help us to do the calculations. It will be all wrong. So use this proper format, 6e negative 6. That's simple. Okay, and then the absorbance values, and then construct your calibration curve, get the best fit line, and we need this equation to do the rest of our calculations. Y equals 24,900x plus 0.0228. Okay, don't use this. Now the next is calculate the molar extinction coefficient for Allura red at 504 nanometers. So here 504 nanometers means the wavelength of the calibration wavelength where the Allura red absorbs the most. So you have nothing to do with this one for your calculations. So we're going to calculate the molar extinction coefficient E from the graph. So for that you need the equation from the graph. For example, what I got is 24,900. You guys also do your own calibration curve and see what number you're going to get. 0.0228. And one more thing you can add to your calibration curve is, you can see here I have not included the very first data, which is 0, 0 to begin with. So you can start that with 0, 0. 0 concentration of Allura red for the first one, since we use water, and then the 0 absorbance. So then the calibration line will go through the 0, 0 margin or the origin. Okay, now back to the molar extinction coefficient. So this is our equation. A equals molar extinction coefficient, B, C is the concentration, X is the concentration, Y is the absorbance, and here this number represent epsilon times B. But remember, what is B? B is the path length, the distance from here to here, which is 1 centimeter. So since B is 1, so the molar extinction coefficient going to be the slope of the graph, which is 24,900. That's the number you're going to write. Okay. And then for the next part, use your calibration curve to determine the concentration of Allura red in the diluted unknown. Diluted unknown is the sample that I explained to you. You took 1 milliliter of Allura red, add 9 milliliters of water. Now you have 10 milliliter sample. To this one, absorbance was given as 0.357. So for our equation, we plug 0.357. So absorbance of this one is 0.357. And our equation, Y equals 24,900 X plus 0.0228. Now for the Y value, you add 0.357. And then you solve for X. 24,900x plus 0.0228, and you will get a number for X when you do the calculation, something like this, into 10 to the negative 5 molar. Now this is the concentration of the diluted unknown or the Gatorade, and we can consider this as our M2 value when we are trying to use the dilution equation. Now this concentration is in a certain volume. What is the volume this concentration in? That is 10 milliliter sample. So the V2 therefore going to be 10 milliliters. And what's going to be the V1? Meaning what is the amount we took from the original Gatorade sample? That is 1 milliliter. So we need to find out what is the concentration of that sample. So V1 is 1 milliliter, M1 we need to find out. So we use V1, M1, V1 equals M2, V2. So our goal is to find out M1. M1 we don't know, V1 1 milliliter, M2 1.342 into 10 to the negative 5, V2 is 10 milliliters. And then the M1 is going to be then 1.342 into 10 to the negative 4 molar. That's how you find out the concentration of the undiluted Gatorade sample. Okay. Next, if you drank 12-ounce bottle of the unknown, how many molecules of Oluvaride would you consume? We are given 1 liter is 33.814. So you use the concentration that is given in moles per liters, 1.342 into 10 to the negative 3, negative 4 moles per liters. Need to convert liters to ounces. 1 liter 33.814 ounces. And if you drank 12 ounce, how much is that going to be? And then you need to convert moles to molecules. 6.022 into 10 to the 23 molecules. Liters, liters, moles, moles, ounces, ounces. So you're going to be getting a number similar to this, 2.88, 2.868. Into 10 to the 19 molecules. So if you drank a Gatorade 12 ounce bottle, you are consuming this many number of dye molecules. Okay, so next time you can think, if you drink any red beverages like Kool-Aid, Gatorade, how many dye molecules you are putting into your body. Okay, 10 to the 19, it's a huge number. Okay, all right, so that's how we're going to do our calculations, and hope you understood all the math and how we did the calculations. And if you have any questions, feel free to email me. Okay, then bye for now.